All right, in our next unit here, we're going to take a look at a couple of theorems. In this first lesson, we're going to take a look at the intermediate value theorem. This is kind of a common sense theorem once we break it down, but it's actually really useful. So, the intermediate value theorem, commonly abbreviated IVT. Okay, so if you just see IVT or if you hear somebody say IVT, they're talking about the intermediate value theorem. It's a theorem that says that a continuous function, okay, that part's key, continuous function on an interval cannot skip values, right? And I mean, that makes sense. If it's continuous, it's not going to be skipping anything. So the intermediate value theorem states that if these three conditions hold, then there is at least one number c on the interval a to b, okay, this continuous interval that we're talking about, so that f of c equals k. All right, so let's jot down these three conditions, okay, and then we'll take a look at visually what this actually is saying. All right, so the three conditions are that our function is continuous on a closed interval. Okay, that's actually pretty key. The word closed interval. We have to be including the endpoints. Okay, the y values of our endpoints, right, f of a and f of b, can't be equal to each other. And then we're saying that k, this y value, is any number in between the two y values at our endpoints. All right, so let's take a look at visually what this is saying here. All right, so the basic idea, let's see if I can draw something here. Right, we're saying we're starting at some y value here, and then the function, I don't know, does something, right, and ends here at b. Okay, so what this theorem is saying, right, is that here we've got some y value at a, and then down here we've got some y value at b. Right? We call them f of b and f of a, right, the function value. So what this theorem is saying is that in between these two y values, the function is going to hit every single y value in between. Right? It could go up above that and it could go down. We don't know that for sure. But what we're guaranteed, as long as this is a continuous function, is that we are going to hit every y value in between. So we can claim that for any c in between these, right? So if we think about coming up here to the function, right, we are guaranteed to hit every single y value in between. Right? And again, it's not only those y values. As we can see here, right, this function goes a little bit above f of a and a little bit below f of b. But what this theorem guarantees us is that we will hit every y value in between. And that seems kind of common sense, right? But the important idea that comes out of this, okay, is let's say that we've got our function that looks something like this. Here's where we start. Okay, and I'm just going to kind of take that same graph that I just drew and just shift it down a little bit. So here's my f of a, and then down here is my f of b. So here we can see that f of a is some positive value. Right? We don't really have any idea what it actually is, so I'll just say that f of a is greater than 0, some positive value. And down here we can see that f of b is some negative value. Right? This y value is something negative. So I'll say that f of b is less than 0. Whenever that's the case, okay, if we know for sure that we have a continuous function on a closed interval such that one of the endpoints has a positive y value and the other endpoint has a negative y value, then we are guaranteed that we will end up crossing the x-axis, right? We will have a 0 somewhere, right? So here, if this is our c value, we can say that the y value is 0, right? This is a 0 of the function. Okay, so this is where the intermediate value theorem is most useful in locating zeros, right? If we can find a positive y value and then a negative y value, we know somewhere in between there we're going to have a zero, all right? So let's take a look at a couple more graphs here. Okay, let's see on this graph here. Okay, first we want to figure out, does the intermediate value theorem apply on the specified intervals for these two functions? So here in this first graph, is there a value of c on the interval -2 to 5? Okay, so I'm going from -2 to 5, such that f of c equals 1, right? So what we're saying is there somewhere where the y value is equal to 1? Okay, well, yeah, right? Looks like right about there, and actually over here somewhere, right? So then we want to think about, well, does the intermediate value theorem actually guarantee this? Right? Does the intermediate value theorem actually guarantee that I will have that value? Here, we want to think about the criteria for the intermediate value theorem. Okay, and this is really important on the AP test. Okay, thinking about these criteria. So, does the intermediate value theorem guarantee this? First, we have to figure out if the intermediate value theorem applies. Okay, we have to see if this function fits those criteria. The first criteria is that f is continuous on our given interval. So, in this case, no, this function is not continuous, right? Here we can clearly see there's a jump discontinuity. So, what we can say, and I'm going to type this out actually, we can say that no, the intermediate value theorem does not apply because our function f of x is not continuous on the interval -2 to 5. Okay, so there was actually that value, right? We were able to find values here such that f of c equaled 1, okay? But the intermediate value theorem did not guarantee us that that would take place. Okay, it did take place. Right? Just because the conditions of the intermediate value theorem are not met does not necessarily mean that our statement isn't true. Right? We were able to find y values that equaled 1. But the intermediate value theorem did not guarantee us that because this function was not continuous. Okay? So let's take a look at our second graph here. Okay, so here, first, is there a value of x equals c on the interval 1 to 6? So I'm just looking at this piece right here, right? From x equals 1 to x equals 6, such that g of c equals 3, right? Such that the y value equals 3. Okay, well, a y value of 3 is up here, right? So, no, right? At no point does this piece of the graph hit a y value of 3, right? So here we would just say no. And does the IVT guarantee a value of c on this interval? Well, obviously not, since we said the actual answer is no, but why doesn't the IVT apply here? This piece of the graph is continuous, right? But the y values of the endpoints appear to be about 1.5 and -1, right? The IVT only guarantees that we'll hit all the y values in between the y values of the endpoints. So 3, a y value of 3 is greater than our endpoints here. Okay, so we can say that, I'll type this out again here. We can say, no, the IVT does not apply because we can write it like this: f of c equals 3 does not occur between f of 1 and f of 6. Okay? So we're saying that this y value of 3 is outside of the range of the y values of the endpoints. Therefore, the intermediate value theorem does not apply. Okay? So down here, this is key. Okay, the two conditions that are necessary for the intermediate value theorem. Right? You will actually, if a question about the intermediate value theorem comes up on the AP test, you do have to cite these criteria. Okay, you have to say, I can use the intermediate value theorem because this is true and this is true, therefore I can say that there is a 0 on this interval, or therefore I can say that this function reaches a y value of 2. Okay, and we'll take a look at actually writing that out and applying that here in a second. Okay, but these two conditions that are necessary. Okay, first, our function f of x must be continuous on a closed interval, and we'll just call that interval a to b. All right, so x equals a and x equals b are my endpoints. And then the second criteria is that f of c must be between f of a and f of b. All right, so we have to have a continuous function on a closed interval, and the y value that we're looking for must be between the y values of our endpoints. Okay, that's how we're going to use the intermediate value theorem. Okay, so let's take a look at a few examples here together. Okay, first, it says apply the IVT if possible on the closed interval 0 to 5 so that f of c equals 1 for the function f of x equals x squared plus x minus 1. So what this is saying is show that on this interval somewhere, okay, we don't actually have to figure out exactly where, okay, but just show, if possible, that on this interval we get a y value of 1 somewhere. Okay, well, first we want to see if this meets the criteria. Is this function continuous? Okay, so first we can say, well, yes, okay, this function is continuous, right, because it's a quadratic. Right, so let's write that out first here. Let's just say that well, that doesn't seem to be working. There we go. Okay. So let's say that all right, I guess maybe this isn't going to work. I guess I'll write this out. So we can say that our function f of x is continuous on our interval 0 to 5 because f of x is a polynomial. Okay, all polynomials are continuous everywhere. Now we want to see what our y values of our endpoints are. So I want to plug in 0 and I want to plug in 5. Okay, so let's do that. Let's say f of 0 will be 0 squared plus 0 minus 1, so that'll be negative 1. Then f of 5. So if I plug 5 in, 5 squared is 25, plus 5 is 30, minus 1 is 29. So the y values of our endpoints are negative 1 and 29. So what we can then say, okay, this y value is in between the y values of our endpoints. Okay, so we can say, by the intermediate value theorem, and we can always just abbreviate that IVT, there exists a value C where f of c equals 1 because our function takes on every value from -1 to 29 on our interval 0 to 5. Okay, so the y values have to take on every value between -1 and 29, where the x values take on every value between 0 and 5. Okay, so let's take a look at 2 more here. So example 3 says, use the intermediate value theorem to show that f of x equals x cubed plus 2x minus 1 has a 0 on the interval 0 to 1. Okay, this is where this intermediate value theorem is most useful. So first, is this continuous? Well, yeah, again, we have a polynomial, right? So this is continuous. So we can first say that f of x is continuous on our interval in question because polynomials are continuous everywhere. Then we want to check the y values of our endpoints. So I want to plug in 0 and 1 into my function. So we can say f of 0 is equal to 0 plus 0 minus 1, so -1. And if I plug in 1, I get 1 plus 2, which is 3, minus 1, which is 2. All right, so now what we can say is by the intermediate value theorem, so by the IVT, okay, since we just showed that our criteria are met, the function's continuous, and the value in question of 0 is in between our two y values of the endpoints, let's say by the IVT, since f of 0 is negative, okay, we'll just say it's less than 0, and f of 1 is positive, it's greater than 0, we are guaranteed, so we can just say there exists, we are guaranteed that there exists a value c where we plug that value in, the y value is 0, okay? This is the most useful application of the intermediate value theorem, finding zeros, right? So, I mean, I don't really know exactly what this graph looks like, but I know now that there's a 0, it crosses the x-axis somewhere in between 0 and 1, right? Because f of 0 is negative and f of 1 is positive, all right? Let's take a look at one more example. And this last example, I think, is probably the most common way you would see this idea pop up on the AP test. Okay, so it says a car travels on a straight track during the time interval 0 to 60. The car's velocity, measured in feet per second, is a continuous function. Okay, whenever you see the words continuous, okay, whenever you see something that says continuous, you should think we're probably going to be using some type of theorem, okay? either this one, the intermediate value theorem, or the next one that we're going to talk about in the next lesson, the mean value theorem. Okay, this is another criteria for that. Okay, but continuous is key here. The table below shows selected values of this velocity function. So we want to figure out, okay, if between 0 and 60 seconds, are we guaranteed there's a time when the velocity is equal to -5? Well, if we look at our endpoints, -20 and +10, well, yeah, -5 is in between those y values, right, of -20 and +10. So what we can write out here, okay, we first have to state that our criteria to use the intermediate value theorem are met, which are the function is continuous on a closed interval, and the y value in question is in between the y values of the endpoints. So we can say, actually, we're going to justify our answer as we write this out, so I'm just going to delete that so I can write this nicely here. All right, so we can just say that there we go. Since our function, which in this case is v of t, is continuous on our interval 0 to 60, and v of 0 is -20, and v of 60 equals 10, by the intermediate value theorem, we are guaranteed that there is a time, since we have a variable of t, we'll say a time t, guaranteed say on the interval 0 to 60, such that v of t equals -5. Okay, so it's actually a fairly simple idea. Okay, we're just saying that, well, the function is continuous. One of our endpoints is -20, the other endpoint is 10, when we're talking about the y values. So we're going to hit every y value in between -20 and 10. -5 is in between -20 and 10, so yes, we are guaranteed that is the case. All right, so that's it for this lesson. Tomorrow in class, we will take a look at some practice on this together.